So the internet and BGP are vulnerable to false injections. How is this handled today? Well, this is handled imperfectly simply by having a detection mechanism where when you install BGP, you need also to monitor what is happening. And in principle, most ISPs are still collaborating. So when one of the attacks I mentioned occurred, then it became visible, for example, through the route servers, that all of a sudden a large fraction of the traffic that was of the routes that were pointing to Google servers were pointing to something else. So that was found post-mortem, so after the fact, by systems that are monitoring the network. What we don't discuss in this course, but what is an important part of any network is when we do a network, we do all the protocols we discussed, plus you put in place a monitoring infrastructure that observes everything that happens. So whenever you will see something abnormal, typically, for example, at Google, you see a sudden drop in traffic for some reason, then you start looking at the logs and seeing what happens. Of course, you would like to do better. What you can do better is authenticate the updates. I mean, here, why was ISP2 saying, I am telling you that EPFL is my customer, which was plain wrong. So there is an infrastructure for that, but it's not practically much deployed today. So the idea is to use authentication by having a public key infrastructure for all the ISPs, and then all messages are signed using mechanisms we've already discussed in other contexts. So you need to sign it at origination. So when ISP2 signs the message for EPFL, then it's easy to see it's really coming from somebody who owns the block of addresses that is allocated to EPFL or not. But you also need to make sure, because there are other attacks. We've seen with BGP, there's not only the origination that could be a problem, but you propagate messages. So you could pretend to propagate messages that you've never received, for example. So you need to sign every modification you do. So whenever you receive a path, it has to be signed by all the ASs that have added themselves to the path, so that you're sure that if I receive a route with paths A, B, then it's really signed by A and signed by B. If it is not, then perhaps someone else has added this path for me. That's the price to pay. So you would need to do that. And of course, the problem is you would need to do the signature and verify them for anything you receive. So that cause is a good business for Cisco, Juniper, and the others to sell routers that have dedicated hardware to read and verify signatures very fast, but we're not yet there. So cryptographically signed BGP updates are the exception more than the rule today. Voilà, that's about all we'll say about BGP. I'll let you discover some of the other things. The only thing I want to discuss last is this one. That's the reason why BGP cryptography is not very much deployed today. That's the number of BGP updates as seen by one provider, it's not a tier one, but almost, Hurricane Electric. That's also the one who gave us the IPv6 tunnel we use in Internet Engineering Workshop. I mentioned 500,000 prefixes for IPv4. We see that I was on the lower end. In fact, today, or last time I checked it, in August of this year, we were closer to 800,000. Right? So we're approaching the million of IPv4 prefixes. So that's the size of the rib of BGP routers. Right? For IPv4. For IPv6, we see that we are way below. We are around 50,000. Instead of 500,000, right? So there's more than one order of magnitude difference. And the reason why there's fewer is not, or the bad reason would be because nobody cares about IPv6, so it's still experimental, which is not exactly true today. But it is because with IPv6 we can aggregate more, whereas much more than with IPv4. Voilà, that's all we'll see for today about BGP. Any questions?
Why is there such a strange growth for IPv6 in the middle of the plot?
I don't know. I'll leave it to you as a research exercise to find out. You can pose hypotheses. It could be that there's a large block of IPv6 address that has been announced and then removed. Those are, I mean, this is several years, right? So this is a period of months. They've been announced because somebody is doing a trial with IPv6, then they stopped doing it, for example. That might be the cause. It might be aggregation also, or it might be that some of those were aggregated. It may be also that the routes have changed somehow, so there were many, many routes to some place, now there are fewer. It's hard to know exactly. Other questions? Then if there's not, we move on to our next topic, which is the application layer. The application layer is, of course, the interesting thing of the internet. That's what we use every day, but it's not the topic of this course. So we don't explain to you how to do an app for Android or for iOS or whatever. But we will see what are, from the networking viewpoint, what there is still a few things that are specific of networking. We'll talk in particular of QUIC, which I could put in the transport layer, but is formally application layer. Then a few things in particular relative to how IPv6 and IPv4 are combined today. The application layer, you did a small application layer in Lab 3 when you did a small chat program with multicast or other programs that transfer data from a PMU to a server. Those are examples of application layers. So this is anything that uses a socket, or those of you who did the optional parts of Lab 3, WebSocket. WebSocket is an example of a higher level construction than the sockets themselves. The sockets are a bit painful to use, as you have seen. So they're higher level construction. WebSocket is one of them. HTML2 is another one, and we'll talk about QUIC in an example. HTTP2, sorry, not HTML. HTTP is the protocol that was originally invented for the web. This is the one that made the internet successful. The internet existed since the mid-70s. HTTP was developed in '92, I remember. And it's only then that people become interested in the internet. Before that, it was a bit like using Linux with the command line. After HTTP and the web, it was more like using a windowing system, a Macintosh, rather than a command line interface. So HTTP 1 was the first version, and HTTP 1 was a very simple protocol. It was a get and put protocol. You ask for an object, which is in fact a file. Inside the file, you have HTML text. If you click on the HTML text, you get another object, etc. That was the very simple HTTP 1.0. HTTP 1.1 improved things by allowing multiple objects to be downloaded at the same time or in parallel using multiple TCP connections. Then people realized that using multiple TCP connections is good for the client. Why is it good for the client? Assume you're downloading from a website, a complicated web page that has text, images, etc. If you use a single HTTP connection, you have to wait for everything to come one after the other. If you use, and you are, while you're doing that, you're competing with all the other TCP connections in the world. If there's a bottleneck somewhere, by the quasi-proportional fair sharing principle of TCP, you will get all a fair share for one connection. If you have multiple connections, you get more because you are handled by the fairness principle as n customers, not one. So you will get a larger fraction of the bottleneck. So it's better for the selfish users. Also, there's also other latency advantages. But for the server, it's much less interesting because servers are bottlenecks. What servers don't like is handling too many TCP connections. I mean, their job is to handle a large number of customers. If every customer has 20 TCP connections, it's like having 20 times more customers. So you prefer to reduce the number. So there was this tension between the two. HTTP2 solved the problem radically by allowing only one TCP connection between server and client, but allowing a large number of requests to be multiplexed at the application layer. So instead of saying, give me this page, I could send a request saying, give me this page and this object and that object. And if each of these objects require different processing on the server, some may require the server to go to a database, for example, they can be handled by the server in parallel. And you have only one connection, which makes the lower layers of the server more happy. Right? This is HTTP2 also provides a very large number of functions to allow things like allow the server to push information, to refresh the page, and etc. So it's very powerful, very complex systems that makes the programming of the application much easier because HTTP2 does lots of things for you. Now, if we look at our interest, which is more on TCP and things like this, assume you use HTTP2, and there are 10 embedded objects that will be processed in parallel by the different elements at the server. Also, servers are typically have hundreds of cores, so they're well able to handle things in parallel. And one packet of the first object is lost. Of course, TCP will retransmit it, but what will happen next? The majority was saying A at first, but the truth is B, of course. If you have a single TCP connection, we know that TCP has the head-of-the-line blocking problem. If one packet is lost, even if all the others were received, of course, they are still kept in the receive buffer, in the socket receive buffer, but they are not visible to the application because the principle of TCP is to deliver things in sequence. This is how TCP is. Right? So even if you've made parallelism at the level of HTML, of HTTP, and you allow the server to process things in parallel, at the end, depending on how the server has serialized the objects in the TCP connection, this serialization will have this head-of-the-line blocking effect. So if you look up Wikipedia or other things, you will see HTTP2 solves the head-of-the-line blocking. If you read carefully, I mean, it should not exactly be true. There is no head-of-the-line blocking from the viewpoint of the server. You send a request to the server. If the request involves multiple actions on the server side, they can be done in parallel because HTTP has mechanisms to put phrases and be able to express those different things in parallel. But at the end of the day, if you have a single TCP connection, we know well that if one packet is lost, you need to repair it before receiving the next one, before reading the next one, even if the next one is still present here. Another question here is FTP. So FTP today is not used very much other than inside the machine, for example, because it's unreliable, but you have SFTP, which is an alternative version, but to simplify, I keep FTP. So FTP is a remote shell into a machine that allows you also to transfer files. So what you do with the historical version of TCP, you open a TCP connection to an FTP server. The FTP server gives you the OK, and you open a second TCP connection on which you do the transfer. So FTP gives you a shell. The first connection is used for having the shell in which you can type the command lines, get, put. And whenever you decide to do a get or a put, another TCP connection is open to do the actual transfer. Right? This is the standard FTP, and there's the so-called FTP passive mode. Right? The question is, which of these port numbers are TCP server ports? So the answer here is not about every port number possible, but if we look at port number 21, this is clearly a TCP server port. If you had to write the program, you would do listen at this point. So the TCP connection is opened by the TCP client. So the FTP server is the TCP server. But the standard FTP has this peculiarity that the FTP server then opens a TCP connection towards the FTP client. Why is that done? Why not? This is how things are. So you see, when you decide to transfer a file, for example, the protocol says that the FTP client should first prepare a socket with a port number here, inform the server about the port number, and then the port number does a TCP connect to this socket that is prepared by the FTP client, which means the FTP client is in fact a TCP server here. This illustrates what the word server really means. It's a word of a given interaction. At the TCP layer, an FTP client is a server. Of course, this is a bit weird, although it has benefits from the viewpoint of performance, because that means this guy can very quickly get things done here. But as you can imagine, there are firewalls that do not like this. One poor man's form of security is to try to avoid having TCP connections being open to random servers. If you have a random server that is accepting TCP connection, probably it's infected. So what quickly happened after this was deployed is that many firewalls prevent this from happening. So if you open a connection from the server to me, the firewall will kill that, will kill the TCP SYN packet, because it accepts only TCP SYN packet only to a small selected set of computers that are expected to be servers. So this doesn't work. FTP doesn't work in many cases. So another version of TCP has been done that does the opening in the correct way, or the one we expect, not correct, both are correct, but in the one we expect, in the sense here that it's the FTP server that will open a port that is ready for receiving a connection, and that will inform the client of this. Right? Probably the idea of this was to make the job of the server simpler. We see here the server does more job. It opens another socket, and so there's more work here. So the correct answer, therefore, is F21 is a server port, and 1, 2, 3, which are server ports, so and 1, 2, 3, 4, 5, 6, this one here. The FTP client port is a server port. So we see also that a server port is not necessarily a well-defined reserved port here. So those are little details on how we organize things in terms of client and server. In the lab, those of you who did that part also have seen that we don't typically do a transfer using TCP, but using some form of authentication and encryption. So the standard way of transferring objects today is not with FTP or plain TCP, but with TLS or SFTP. So we add to this basic transport mechanism a layer for authentication using certificates, as we have discussed in other contexts, and encryption. That's the standard way of transferring information today. So when we use HTTP2 or HTTP1, typically we don't do it natively over TCP, but over TLS. So TLS, we won't go through the details of that. That's the job of the course on security. But from our viewpoint, what it does is it allows all the information that's sent by TCP to be encrypted using secret keys. And before sharing and agreeing on the secret keys, one of the ends authenticate the other, or possibly both ends authenticate them using certificates. For example, if I go to my bank here, I will use the HTTPS. If you use HTTPS, that means you will use TLS. And in principle, that means the port number is this one. And you trust your browser to show you whether the place you're going is using TLS or not. If it's using TLS, it will show a padlock, a closed padlock, for example, here. That means the identity of this site has been verified. So I'm truly speaking to my bank and not to a man in the middle that is taking all the information. We'll change the destination IBAN and we'll do the transfer not to the Office of Taxes, but to one of you in the room who will receive the money. I believe I've paid my taxes, but you receive the money. So that's what you want to avoid by making sure that the thing is authenticated, and it's also encrypted to avoid other people from reading it, and also from transforming it. Now there's a price to pay for that, and if you use the standard version or the most widespread version of TLS, this is all the things you need to do before exchanging data. So we see that there is at least 1 and 2 round trips, plus a bit of processing time, before being able to exchange data. So now assume you put all of this together. How many handshakes? So a handshake means a complete round trip of including the processing. Do we need before I can send 1 bit of information? Well, the correct answer is more than you think, because I mean, we've seen that TLS takes at least 2 handshakes, but also you need to open the TCP connection, which requires at least 1 handshake, a SYN followed by a SYN-ACK. Right. So in the best case, you have 3 handshakes. So the correct answer is at least C. Now, if you're unlucky, it can even be 4. Which means that whenever you get to a site, or to a Google search or whatever, you have 3 handshakes, 3 round trips of information before actually exchanging information. So typically if you go to a site, it's because you want to ask a question or get something, so you'll have a 4th handshake, which is the true information you want to send. Right? That's perceived as a problem today, so that's a problem. So the problem is solved first by fixing TLS. So the newer version of TLS do everything in 1 handshake. You can ask why they didn't do it at the beginning. Well, probably at the beginning they didn't care. So by looking at things more seriously, also by reducing the cryptographic system that can be used, it was possible. We won't go through the details. But then, even if we reduce to 1 handshake, we still have the problem of having now 2 handshakes. So before sending your request to Google, you have ping, pong, and ping, pong twice. Right? So this motivated Google, in fact, and others, to develop an alternative to TCP, which is trying to do all the things we have seen today together. What did we see today? Well, today and the weeks before, we've seen we need TCP for lots of reasons, for making the data transfer reliable, for making congestion control, and relieving the job of the programmer. But we've seen that the programmer's job is not so easy, so people have developed HTTP2 to make the interaction a bit richer, and WebSockets that we've seen in the lab that is also similar to HTTP2. And then there's TLS in the middle. And if we put all of this together, well, first we have layered many things that cause a latency performance penalty. That's the first thing. And second, we still have this head-of-the-line blocking stupid problem that if I'm downloading a page or I'm sending something, and 1 packet in the script, for example, that should display a stupid things like an animated GIF or something, if that thing is missing, the page is blocked, right, until you see the complete page. Right? So you'd like to avoid this. This is the job goal that motivated the development of QUIC. So QUIC is formally an application because it uses UDP, but it is really playing the role of a transport layer. The goal of QUIC is really to replace TCP from a programmer's viewpoint, and it does replace TCP in the sense that QUIC does not use TCP and implements practically all the things that TCP does, but as we will see, with little variance to avoid, in particular, the head-of-the-line blocking. So QUIC uses TLS 1.3, and it runs over UDP. So the major thing it does is first to avoid having, through the layered principle, if we run TLS over TCP, first we open a TCP connection, then we open a TLS session, or security association. Here, because we don't have TCP and we are Google, so we develop everything, we do everything at once, which means in a single handshake, in a single exchange of message. We do something that is both sharing, putting in place the cryptographic means we need to do authentication and encryption, and all the things that TCP was doing, which is to contact a server and make sure we agree on a number of things for the sliding window, for example. So you do everything in one shot here. So it's implemented in all the Google apps. If you use including the Google web browser, then of course it will implement this. It's not implemented in the other browsers like Safari or Explorer, but you can try it with Wireshark. You will see that most of the traffic you will see when you handle with Google will be using QUIC and not TCP. The major difference between QUIC and TCP, so one major difference is it avoids doing two handshakes, first opening a TCP connection, then security association. It does everything in once, which from the Google viewpoint is a huge benefit because it means the latency and the job of also the servers is considerably simplified. For us, from the viewpoint of what we've seen before, there's another more subtle benefit, which is that QUIC has the concept of streams. So it solves the stupid problem of TCP that delivers things in sequence. QUIC does that, but per streams. So the sequence is guaranteed only for inside objects. So if you transfer from a file for a web page, a video, an image, or several images, plus a JavaScript, plus some HTML text, each of those objects will be transferred typically in different streams. Inside the streams, things will be like for TCP, but across streams, the streams happen in parallel. So if one packet of the stupid animated GIF that is useless and is catching your attention in the corner, if that is missing, the rest of the page can display. So that's the major difference, which of course comes at the cost, which is illustrated here. QUIC packets, which is over UDP, will contain some header, a bit like a TCP header, that is followed by a number of stream data. One stream is used for control. It's called stream 0. That's the one that's used for agreeing on the cryptography keys, for example. And then there are a number of stream data. So QUIC packets contains what is called frames. So a given amount of data. So typical packet will contain only one stream plus stream 0, but if some data of some streams are very small, they can all be merged in the same packet here. QUIC uses still the concept of connection, but a connection is only for the global thing. Other than that, it does the obvious thing. So differential encoding applies here well. It uses all the state-of-the-art on TCP, but does it at the appropriate place. For example, every packet is numbered, and every lost packet is detected and and the missing data will be retransmitted. To avoid many of the ordering problems we had with TCP, there is a packet number which is per packet. So every QUIC packet has a packet number. And the packet number has nothing to do with the byte offset that is here. In TCP, the packet number, there's no packet number, but there is a sequence number inside the TCP, which is the offset of the bytes in the original block of data that's written by the application. So the packet number is the offset. Here in QUIC, we do the two separately. The offset will be written in the header for the streams, but the packet number is a number of this packet, and every packet is unique. If you retransmit some data because it was lost, it's a new packet. So you will not have to worry about all the subtle problems we had with TCP on trying to infer whether this is a retransmission or not. The packet number space is 64 bits. If you do the calculation, 64 bits gives you a huge number. Even if you send one packet every millisecond, I believe it will take millions of years until you wrap up, right? So this space is very huge, so every packet is a unique thing with this numbering. Other than that, retransmission are done with mechanisms exactly similar to TCP. So with obvious advantages, because now you have lots of space. So, for example, the acknowledgement frames will say exactly all the things that are acknowledged. So for every stream, which bytes have been received and which not, so that you can know exactly what has to be retransmitted. So a lot of the heuristics we had in TCP to try to infer whether this is missing or not become unnecessary here. So we expect the performance to be better. Congestion control is the same as TCP Reno or Cubic. I say Reno or Cubic. There are multiple versions of QUIC. There is obviously QUIC was pushed and deployed and invented by Google. So Google has its own version, which uses Cubic. Then Google went to the IETF to make it a standard, and the standard version uses Reno. And that's, so there are multiple versions of QUIC here. In principle, although we don't see many implementations, QUIC also allows to have unreliable streams. So streams on which you don't care to retransmit if data is missing. For example, for a real-time application that is constantly refreshing the information. Here is an example of a master project that was done by one of their predecessors last semester. She called it Ephemeral-QUIC. We had, and we still have, a PMU streaming application that sends one measurement every 20 milliseconds. Today, or the state of the art is to use UDP for that, because if you use TCP, as we have discussed multiple times, you have the head of the line blocking. If one measurement is missing, you will retransmit it, that's fine. But if the retransmission takes long, that will block the next measurement from arriving. And if one measurement is lost and the next has arrived, you prefer to have the next and lose this one because there is newer, more fresher information. So TCP would have head of the line blocking, so typically you don't want to use it, so you use UDP, but if you use UDP, you have to code yourself the reliability. I said you don't care about repairing a loss if a new thing comes, but if your round trip time is not very small but not very large, for say 3 milliseconds, that's the typical round trip time we have in those settings. If a packet is missing, you detect it after 3 milliseconds, still is a good idea to retransmit it. But you don't want to retransmit it forever, like TCP will do, if there is a new one that comes. So you want a mechanism that says, I transmit a packet or a stream of data. If that data is not acknowledged, I will try again to retransmit until new data comes. When new data comes, I abort the attempts to retransmit this thing because whatever I have to retransmit is the new. TCP is unable to do that. TCP will insist on repairing the first missing byte before allowing you to send anything else. With TCP, with QUIC, it's easy to do by sending one stream per packet. So one measurement is one stream. One of the beauties of QUIC is that the streams are very lightweight things, and creation of a stream requires no overhead. You just send a packet by putting an increasing number in the stream ID. So those are the kinds of things that we can imagine doing, and I guess in 5 to 10 years from now, it's well possible that QUIC will replace TCP for many things. It's a bit too early to say now, but QUIC or something like QUIC is certainly better than TCP. Yes, question?
You told that many Google apps, they already use QUIC.
Yes.
And it means that many servers already support QUIC.
Yes. Yes. If you use Safari to go to Google, Safari doesn't support QUIC, so they will use TCP. But if you use Chrome, it will use QUIC. Or if you use an app, the YouTube app, you probably will use QUIC. Question?
In the previous slide, it was written in support the Untitled IP.
Yes.
Does it mean that it tracks you even if you do not IP, and then it will be again?
Where did I put this? Yes. One of the things is changing the IP address. Why do we care about that? Why do you care about that? Exactly, because of mobility. So typically you might flip from one address to the next. And what happens today if you do that? If you're downloading something, well, it's up to the application layer to take care of that. So if you use Apple software, most Apple software will detect it, will see, oh, this transfer is blocked now. It will put a resynchronization point, wait until a new socket is available, and will continue from there. But the job is done by the application layer. If you use, even on an Apple system, a non-Apple software, probably when you do this, you change your IP address, you reconnect, it will consider that the transfer failed and will restart from scratch. If you're transferring a video of 10 gigabytes, it's very irritating. So one of the desire that everybody has is if you change IP address, you would like to continue the TCP connection. With TCP, it's not possible because TCP is hard-coded with socket. The socket is identified by an IP address of the remote part. If you change if the server sees a change of IP address, it cannot be the same socket, right? So it's a problem that people have been trying very hard to solve over the years. And QUIC says, well, we support that. So we give because we have incorporated a higher level than the IP address, which is the identity we have with the certificates and with the authentication mechanism. So I can share an identity of my connection that is associated with an identity of endpoints, which is cryptographically verified. And then I can agree that this is the continuation of a previous thing. At least in theory. So that works. But I give in the slides examples where a change of IP address might cause some problems. There are still some attacks that are possible even with QUIC. So it is possible, but not in all cases, right? Other questions? Then if there's no question, let's go to perhaps the most visible part of the internet for many people. That's the DNS. Well, we've seen it all the time. At the origin, the DNS, so the DNS uses names and has a hierarchy of names. At the origin, there is a virtual thing called the root, and the three-letter domains were all the historical domains. At the origin, there was only this, .com for commercial, edu for educational sector, universities, etc. Two-letter domains are countries. And then recently, it has opened anything. So you can, if you're called Mr. Dupont, you can buy the domain Dupont, and then you can sell subdomains to Dupont, of course. Right? What we're more interested in is how it works. What happens really when we have an interaction here. So let's see an example here. When you are sitting on a computer and you connect to this thing here. I'm not showing HTTPS, of course, there will be also other. So I want to go to a machine that's called zurich.ibm.com. Right? Mentally at the origin, the goal of DNS is to replace IP addresses by names, like this one. So I know where I'm going. What will happen, of course, is my machine doesn't know what is the IP address. So the job of my machine is to find the IP address that corresponds to this name. So the first thing my machine will do is have a part of the program, which is the client resolver part of my web browser, that will go to my DNS server. I must have a DNS server, and we've seen when we talked about IP configuration that this is part of the configuration of your machine, to have a DNS server. So my machine will send to the DNS server a query, a DNS query, that's a message, saying what is the IP address of this guy. An A here, label, means IP address. address. Right? We will see that there are IPv4, which is an A, and IPv6, which is quadruple A, right here. Now, my server probably doesn't know. My server, the server of EPFL, I guess this is time for linear algebra. So 1 more minute. The server, the DNS server of EPFL knows in detail all the IP addresses of EPFL because it's managed by the EPFL networking people. But it doesn't know all the IP addresses of the world. It will know by learning. Okay, so we will learn next week how the DNS server of EPFL gets all these addresses.